this elliptic curve project where you get it becomes a lot more concrete. So remember, your elliptic curves look like this: f cubed plus ax plus b mod p, and p is a prime number. So now, remember, it's kind of weird to find the points on the curve. So what you have to do is these two things to install the library we need. So when you do those in this environment, you have to put an exclamation point on them. This just downloads an elliptic curve library from my website, ecc.py, from my GitHub repository. I just got it somewhere and put it there. And this installs NumPy. So that's going to prepare us to do what we need to do here. All right. And so let me just run that first. And while that goes, I'm going to go back here. All right, so now we're going to, like we did with RSA, we're going to use a really simple case that's of course not secure with really small numbers so we can see it. So A is 1, B is 2, and P is 5. So it's x cubed plus x plus 2 mod 5. And so if x is minus 1, then this is minus 1 cubed is negative 1. This is minus 1 plus 2, they get 0. So y squared is 0. So that's a solution, minus 1, 0. And you can also write that as 4, 0, because we're working modulus 5. So minus 1 is 4 mod 5. All right, so you can say the point 4, 0 is on the curve. And now you can determine whether a point is on the curve using the onCurve function. So this will check that point 4, 0 to see if it's on the curve. So we don't need to run the Python 3 command because Google Colab is already a Python 3 environment. It's downloaded this stuff and installed it. So now I can run this. Let me make my font bigger to make it more clear there. So this is just this defines the curve. This is the point I'm going to check, and I'm going to use the onCurve function that I imported there to tell me if it's on the curve. And it's going to tell me it's on the curve. Okay, so now I can find all the points on the curve. So I don't need to import this again. I can just use this part. And all I'm going to do is I'm going to go for the x and the y for the range of p. Remember, all the numbers go from 0 to p minus 1, and that's what range of p does. So I'm going to try all values of x and all values of y. Only integers matter. So the total number of possible points is p squared, but there's only going to be a smaller number of them that are on the curve. So I'm going to try all possible points and see which ones are on the curve. So I'll make another block of code here. There we go. And so it doesn't take long. And as you see, there's only 3 points on the curve: 1, 2, 1, 3, and 4, 0. And this one has 25 possible points. Out of the 25 points that exist, only 3 of them are on the elliptic curve. All right. Now, we'll change B to 1 and see what happens. If we change B to 1 and don't change anything else, then we get a lot more points. So this again, there's 25 possible points, but now there's what, 6, 8 of them are on the curve. So, that's, there's no simple relation. These elliptic curves are a little complicated that way. So there's a couple of flags to find here. And then we can consider, say, scalar multiplication. The library we're using has this function, scalar multiplication, that will multiply a point by k. And you have to give it a, b, and p, which define your curve, and you have to give it the x and y of the point, and k. So now, we've done this before. We found the points on this curve, 1, 1, and 5. And now we're going to try various multiples of 0, 1. There's various points here, but one of the points on the curve is 0, 1. This is the one we just ran with about 8 points on the curve. So now we're going to try multiples of that point, 0 and 1. So there's all the points on the curve. And here's, I guess I have to go up here. There, okay. And here I'm going to do up to 15 multiples of from 0 to 14. So here we go. 0 times it is nothing. Then you get 1. Here you get 4, 2, 2, 1, just printing out in sort of an ugly way. But you can see, and 3, 2, and here you're getting 4, 2, 2, 1. Notice there's a repetitive pattern. If you multiply by 9, you get none, none, and from then on, it's just repeating the same series. 0, 1, 4, 2, 2, 1, and so on. So the total number of points I got was 1, 2, 3, 4, 5, 6, 7, 8. I generated all 8 of the points here. So 0, 1 is a generator of the curve. You multiply it by numbers, you'll explore every possible value. All right. And I don't know why it printed these points in an ugly form on my printout, but that's, I could probably fix that, but it doesn't really matter. So this is going to list multiples of all 8 points on the curve. I'm going to go through all 8 points and then multiply them 10 times to see what we get. And so I'm going to be able to see which points are generators of the curve. So here I'm getting, okay, there we go. So this is what I did before. If I use 0, 1, I'm going to get all 8 points. The none doesn't repeat until I'm down to 9. If I do 0, 4, looks like, again, I get all the points. The none doesn't repeat until down here. But if I do 2, 1, I have a short loop. It just repeats here and repeats here and repeats here, so I don't get to generate all the points in the curve. And this is what they said. You don't want one of these ones with a short loop, or it would leak out information for generator. Here's another one that's not a generator. The none repeats every 3 times. And this one is a generator. The none doesn't repeat till the end. This one's a generator, and that one's a generator. That one. So most of them are generators, but a couple of them were not generators. All right. So, and then we can do elliptic curve Diffie-Hellman, and I think this is as far as I'll demonstrate live. So we're going to make a curve with a bigger number, 17 here and 7. We're going to move to a bigger curve to get a little more interesting situation. And here, we're going to confirm that there are 17 points on the curve, and we're going to discover that 15, 4 is a generator. So let me run this. All right. So this is just going to check all the possible points, which is 17 squared points, so several hundred, 300 and something, I think. And then it'll find out which ones are on the curve, and then we're going to see if 15, 4 is a generator. So the number of points is 17, and there they are. And one of them is 15, 4. If you go over here, 15, 4 is one of the points on the curve. So I'm going to try multiplying it by various numbers. And as you see, I start with none, none for 0. And I don't see that 0 again until 18. So I got all 17 points on the curve before it repeated. So I've proven that that number is a generator of the curve. Now I can do key agreement. One end chooses a secret of 4, then multiplies 4 times the generator and sends that across the wire. This person chooses a secret of 7, takes 7 times the generator and sends that over the wire. Each one of them takes their secret and multiplies it by the number that came over the wire, and that's going to get you to 112. So that's how it works, and that's what I wanted to show you. And there's several flags to find here, and a couple more exotic things later having to do with signatures. But you know, I think that's enough. I'm not going to go through all of it because, like I say, this is legacy information. This is what we are using now, and we should continue using for maybe another 5 years, but we all should be moving away from this to the quantum proof algorithms instead. So it may not be worth struggling through all the details of elliptic curve cryptography, but this much gives you an idea how it works. So that's what I